We're gonna look at recursive programming, see how to write and formulate the recursive functions. So here is our example. We're gonna compute the factorial expression. So let's start by writing out the factorial of n. Here it is all the numbers between n and 1 are multiplied. So n times n minus 1 times n minus 2 all the way down to 1. Alright, so this is what we are required to do. The function is gonna compute n factorial provided n. This will be the parameter going into the function. The function will compute this expression. So one quick thing to note here is you can do this in iterative way without recursion. If you want to do iterative way, you can write a for loop, have the for loop count from 1 up to n, multiply everything together. So remember, this would be iterative if you use for loop. If we're doing recursive, that probably means we're not gonna do the for loop necessarily. The recursion means the function is gonna call itself, right? So the function is gonna call itself. This means we want to reduce our problem, the factorial, to a factorial problem of smaller size. So this is how the function can call itself. If I start with the factorial function is gonna call the factorial function, but with smaller input. The problem size is gonna become smaller and smaller. So to put that into concretely in concrete words, what does that mean? So this is the expression n factorial, and if you look here, you can see that this is n minus 1 factorial, right? Here I multiply all the numbers between 1 and n minus 1. So I can spot a small factorial problem within the big factorial problem, which will be my formulation. N factorial is equal n times n minus 1 factorial. So if you think about it, like, why are we doing this, or why is this good? Because if I ask somebody what is 4 factorial, that's what they can answer me: 4 times 3 factorial. And obviously next I'm gonna ask them what is 3 factorial, so they're gonna answer it's 3 times 2 factorial. And next we're gonna ask what's 2 factorial. It is 2 times 1 factorial. And at that point the problem is too small. 1 factorial is a trivial case. We know the answer, right? 1 factorial equal 1. Also 0 factorial equal 1. So we're gonna call these base cases, base case or trivial case, right? So it means when the problem size become too small, I don't need to do recursions anymore. With 4 factorial I had to do recursions, but when I reach 1 factorial, I reach the base case, I know the answer. This is what we call convergence. So obviously we want our recursion to converge, right? So what do we do back then? Remember, we're not done at this point. At this point, all of these guys are on the stack memory. So at that point, I know the answer to this. I will substitute here 1, right? Let me do this. I want to keep this guy up there. Let's keep this here. So at this point, I know that 1 factorial is 1. So I will go there and substitute by 1. I will compute this, which is equal to 2. So now I know that 2 factorial is 2. So I'm gonna replace it here. 2 factorial, I'm gonna have 2. We're done with this. Let's take care of this. 3 times 2 is 6. Now I know that 3 factorial is 6, so I'm gonna replace that here, right? And finally I will compute this guy, 24. I know 4 factorial is 24, which was my original answer. So what you have just seen here is when we were working with the problem downwards, we were pushing things on the stack. When we are building the solution back, in back substitution, we are pulling things off the stack and building the answer. So the stack, just think about it as memory. This gonna use the memory, the stack memory is gonna grow during the calls. So I think that's good enough for the theory of it. So we know now how it works. How about we move a little bit to the code? So to write the code, that's all you need to have. You need to have our formulation, and you need to have the base case. So basically what you see here, this is really the code. The code is gonna exactly mirror this case. Alright, let's move over to the code side. So here I have an empty program. Let's make sure it runs. It does. Alright, let's start from scratch. Recursive functions. How about we do a header here, put the prototype, int factorial, int, no need to write the term here, right? This is just a prototype, you don't have to fill the name. So this is the prototype. I can write my function here. Alright, so here is our function. Parameter is n. So when we code this function, we typically start with a base case. So let's take care of this. Base case, I have two base cases. So here is the base case. If n is either 1 or 0, the answer is 1. If n is 0 or n is 1, return 1 and we're done. Otherwise, I need to program this guy. Otherwise, the answer will be n times. For this guy, we need to call the function again with parameter n minus 1. Factorial n minus 1. But remember, that guy returns something. So I need to do return. Right? So the answer that we either return 1 or we return n times factorial n minus 1. Just by looking at these things, you can easily see this is a recursion, right? Because factorial is calling factorial. So very clearly this is a recursive function formulation. There is no loop. So it looks a bit different, right? There's no loop in there, but this is gonna call multiple times, which is kind of what have effect of loop or type of loop. Alright, so that's it. Usually recursive functions a lot of time are very small. You can see here not much code. There's not much code in there. Alright, so let's review our work so far, see what we've done. So the most important part was to formulate the factorial into a factorial of smaller size. So once we got our formulation and we know it works, we obviously gotta have base cases, because you don't want the recursion to keep going on forever, which will be like an infinite loop. So we got our base cases, and typically when you write the code, you write the base cases first, right? So that's why I took care of the base cases first. If not, then we're gonna do the recursion. Alright, so testing this should be quite straightforward. We're just gonna call the function basically. Here is a parameter and result. You can declare these as unsigned long int because factorial grows quickly. But today I just gonna use int because we're focusing on the recursion, not really on the big data type. So let's keep that simple. Alright, so we're reading an integer from the user, calling factorial, and printing the result. Let's double check. Right, we're gonna read the integer into n. Result is factorial of n and print it out, see what we got. Alright, let's run this. Factorial 0, that's the base case, we know that. factorial of 1, that's the base case. Alright, 2 is 2, that's good. Factorial 3 should be 6. Factorial 4 is 24. And factorial 5 is 120. So it's working well. So that's good. Got our code to work. Alright, so there's one last thing we're gonna do with this code, is we're gonna see how to trace the factorial. We know that if it runs correct, probably it's correct, but sometimes you want to be able to trace it on a piece of paper to see how it works, to see how exactly the code works. So let's move over to this side and trace the function. So the procedure we do with factorials to trace them is we're gonna write this function multiple times, because if you think about it, the factorial calls the factorial. So if this is let me go back here. So remember, if you start with factorial 4, it's gonna call factorial 3, it's gonna call factorial 2, it's gonna call factorial 1. So what this is saying is this function will be called 4 times. So there will be 4 instances of this function. So we're gonna draw all of these 4 instances to see how they react with each other. So let's trace the same example. So here is my original call. Factorial 4. So what would this guy do if I call with parameter 4? If n is equal to 4, we're gonna do this. Return 4 times factorial 3. Return 4 times factorial 3. So obviously there is f of 3, function call with 3. Let's take care of that here. So what would this guy do if you call with 3? It's gonna do return 3 times f of 2. Return 3 times f of 2. Let's do the f of 2. It's gonna do returns 2 times f of 1. Return 2 times f of 1. And finally, let's do f of 1. If the parameter n is 1, this is the base case, right? So it's simply gonna return 1. So let's return 1. Just like we were saying, if you call f of 4, the function will be called 4 times. There will be 4 instances, which is what you're looking at here. Now let's go through them. So so let's start at this point. F of 4 return 4 times f of 3. Before we resolve this, we have to resolve f of 3. So we're gonna immediately come to this point, right? It's gonna lead us to here. Alright, so let's solve f of 3. Return 3 times f of 2. We're gonna put everything on hold, immediately go to here. Same situation is gonna occur, right? F of 2 return 2 times f of 1. So we're gonna show up here to solve this guy. And the good news, this is the base case. F of 1 will return 1. So where does this 1 go? The 1 is gonna replace this guy, right? Because f of 1 has returned 1, so this is equal to 1. Now we're gonna compute. We are actually computing on the way back. 1 times 2 is 2. Return 2 in place of f of 2. So this guy will be equal to 2. 2 times 3 is 6. Return 6 in place of f of 3. So this is 6. 6 times 4 is 24. So finally that guy is gonna return 24. And this will be the final answer. So think about this for a second. What's the technique that we really learned from the tracing? Is that it's a very good idea to write all the instances of a function. That guy will be called 4 times, so probably we need to write it 4 times and see how the calls interact with each other, and finally go back to building the answer. It's a bit different from tracing iterative code, right? In iterative code, you just write variables and their values underneath. But here we're gonna write the multiple instances to get you a clear picture of what's going on. Alright, so I think this is good enough for this exercise.